Hi, this is Isaac Higgins, reviewing my first out of 3 research papers for the course Engineering Self-Adaptive Systems. This first paper is called The Elastic Node, an experimentation platform for hardware accelerator research in the Internet of Things. It was written by Gregor, Alwyn, and Christopher at the University of Duisburg, Essen, in 2019. Adaptive hardware acceleration has a massive potential for use in autonomic IoT applications. However, developing and experimenting with accelerators in embedded environments is still very challenging. Currently, if an IoT device requires additional computational power for things such as machine learning, it must offload this task to either an alternative edge device nearby or a cloud computing solution. This increases latency and has a potential of failure if the edge device or cloud service is down. If developers of applications or IoT solutions desire additional computational power for machine learning, there is no option to do so on the device itself without using too much battery, as a lot of IoT devices run off battery power. Although there could already be many great use cases for being able to perform hardware acceleration on IoT devices, it is not yet in high demand as developers have either gone without the ability to push the device's computational power beyond battery capacity limitations, or they have discovered alternative solutions to cope with the inability of the IoT device. This solution, however, will potentially be well received by the open source community wanting to better IoT experimentation and energy efficiency in software development, regardless of hardware knowledge and ability. Many projects have aimed to create development platforms for hardware acceleration in the Internet of Things, but none of them have fulfilled the requirements that these authors have set out to adhere to. None of these past papers would allow the gathering of performance and efficiency data from the real-world deployment, which was one of the requirements set out from the start. Many past projects involve a higher energy footprint and consumption, which also doesn't adhere to the requirement that it must be able to last between a few days and a few weeks on a single battery charge. Other projects include the reliance on high-end interfaces, such as PCI Express, that are not available on the low-energy microcontroller unit, or MCU, and field programmable gate array, or FPGA, used in this project. Others are built upon full Linux operating systems, but the objective in this project is to make it simple to develop applications on. The main idea in this paper is to develop an experimentation platform which consists of a wireless embedded device with an 8-bit microcontroller and a low-energy embedded FPGA, as well as an abstraction middleware layer. This platform will empower researchers and software developers without hardware design knowledge to experiment with adaptive hardware acceleration. In doing this, it will enable these users to not rely and depend on offloading workload peaks to nearby edge devices or cloud services that may be unavailable, fail, or have high latency, but instead it could just make these workloads able to be completed locally and in a low latency and reliable manner. A side benefit of performing these computations locally is the added privacy and security of not sending the information elsewhere, where it may be vulnerable to unanticipated access by other entities. The main requirements and scope includes having a flexible support for real-world deployments, which means the hardware needs to be small enough to allow for embedded scenarios, cheap enough to deploy multiple devices, and support mobile experiments and portability. Also having dynamic in-field accelerator reconfiguration and control, which means the user must be able to switch between different accelerators dynamically. It must have easy and fast accelerator access, which means it should be able to be easy for developers to interface with an accelerator, allowing them to develop and change experiments with little effort and increases accessibility. It must have an onboard energy management because energy efficiency is a major concern for battery-operated IoT devices. So it is important to have the ability to monitor accurate energy consumption of the device during experiments. And lastly, it must have easy and low overhead accelerator reuse, which means existing accelerators should be reusable by other researchers, allowing them to easily recreate experiments and compare with previous work. Additionally, researchers will not be required to be experts in hardware accelerator development to use existing accelerators in their own systems and research areas. This is better than what's currently available and the literature that has been written to date, because the authors have incorporated an abstraction layer to bridge the gap between the application and the hardware function. This means that it is easier for the developer to call functions on the FPGA, as it only requires a single line call instead of multiple parts and functions to call, as this is all abstracted away and hidden and performed by the middleware. This allows the developer to not need to implement or consider all the necessary intricacies of calling a function on the FPGA to just focus on what their application needs to do. This solution is also better as it allows for low energy consumption and higher efficiency, allowing the devices to be run on battery power for extended periods of time. The efficiency and power consumption of the Elastic node was evaluated with results in this table of power consumptions of each component of the platform. It is concluded by the authors that a typical 3.7 volt battery could last between 3 days for full utilization of the resources and 2 weeks in less demanding scenarios. And that if a longer lifetime is required, a battery with higher capacity could be used. For evaluation of the accelerator access performance, the latency was measured for a hardware function call, and the total offloading latency was shown to be reduced from 0.14 milliseconds to 0.03 milliseconds, improving the responsiveness by 77.4%. This is a vast improvement in the latency and aids in the efficiency and lesser wait times for function calls. The accelerator startup latency was just a measurement of how long it took to start up the accelerator. This ended up being about 94 milliseconds. The time it took to switch between accelerator, between different accelerators, unexpectedly, was exactly the same as the startup time. This was suspected to be because the switch accelerator. This was expected to be because to switch an accelerator, it is basically like turning off the current accelerator and starting up the new one. Accuracy was another thing that was measured and evaluated. This was measured by using an oscilloscope connected to the sensing resistor. It was observed and the measured value was consistently in line with the true value, and it was concluded that the performance was more than adequate. This was a very well written paper that covered more than was expected. This was a brilliant project idea, and the authors did a good job of completing it thoroughly, making sure they evaluated everything they could about the design and performance of the platform. If I had to give a critique of this paper, it would have to be that there was some inconsistency in the grammar, particularly with pronouns. This alluded to the idea that for one or more of the authors, English might not have been their first language. Thanks.